Part B, well, we can talk about part A since we're here. Part A is just really straightforward, right? How many people are in the auditorium when the concert begins? So that's at t equals 2 because we just got people entering. So part A should just be the integral from 0 to 2 of r of t dt. And I don't know what that came out to be. But yeah, part A of those is usually like that. Part B, to find the time when the rate at which people enter the auditorium is a maximum. And so people enter at this rate, and so we want when the rate is at a maximum. So that's just taking the derivative of r and setting it equal to 0. So r prime equals, what does that equal? Well, let's just say when does r prime equal 0, since you would have had a calculator for this. And r prime equals 0 between 0 and 2 at t is about 1.36296. And then since we're talking about a closed interval and we want the actual max, we'll also have to check at t equals 0 and t equals 2. And so we just need to see which of those are of 1.36296, r of 0, and r of 2. We just need to see which of those three is the actual largest. So r of 0, you can see easily enough is 0. R of 2, if you plug that in, came out to be 120. And r of 1.36 whatever came out to be 854.527. So at this value, 1.3 whatever it was, is where we had the rate at a maximum. Does that make sense for part B?
Yeah.
Cool. Then somebody was also asking about part C for this one. So for part C, we've got the total wait time for all the people in the auditorium. And we find that by adding the time each person waits, starting at the time the person enters the auditorium and ending when the concert begins. So then they give us a function w that is the wait time for all people who enter after time t. Then they give us the derivative of w, which is 2 minus t times r of 2. And they just want us first off to find w of 2 minus w of 1. So w of 2 minus w of 1, well, we could think about that as the integral from 1 to 2 of w prime of t dt. And because the integral of w prime is w, evaluated at the upper limit and evaluated at the lower limit. And so that ought to just be the integral from 1 to 2 of the function they gave us, which I believe was 2 minus t times r of t. And you would just plug that into your, we'll get a nice easy answer for that. Plug that into your calculator, and it came out to be 387.5. Does that make sense for part C? How to set that up? Okay. And then for part D, it says on average, how long does a person wait in the auditorium for the concert to begin? Consider all people who enter the auditorium after the doors open, use the model for the total wait time for part C. So we're looking for an average here. So that's going to be a 1 over should be 1 over our amount from part A, which I guess I should look at our scoring guide. That came out to be 980 for part A. So the average that a person waits is just the total amount of time waited divided by number of people that were waiting. So the total amount of time waited should be the integral from 0 to 2 of W prime, right? Because W is the total weight for all people that enter after T. So we should be able to say it should be integral from 0 to 2 of W prime of T dt, and then we'll divide that by the total number of people that came to this thing at 980, and that should come out to be 0.775 hours on average people waited.
Is that just the normal mean value theorem for integrals, or is that different?
No, that is not the normal mean value theorem for integrals. That is, people are saying things in the chat, and I did not see any of those. I'll have to go back and answer those questions. No, that is not the normal mean value theorem for integrals. So it's just asking us how long does on average, how long does a person wait? And so the total amount of time waited for all people, right? This is the total wait time for all people who enter the auditorium before time T. That's what W represents. And so if we can figure out what W of 2 is, we should be able to divide that by the total number of people that were in the that showed up to the concert. And to figure out what W of 2 is, we do the integral from 2 to 0 W prime, because we know that the value at 0 is just going to be 0. And
so if you messed up those two values on your previous answers, would you still get the point or no?
You could still get the points. Yeah, you still get those points. Yep. Okay, let me go back through the chat and see what everybody has said here. Okay, so could I go over slide 4 from question C? I'll do that. How do I enter that part into my calculator for part B? So for part B, I mean, you just would find the derivative of this. So, I mean, yeah, it's pretty easy derivative to find. What is that, 2,760t minus whatever that is. Find that derivative and then graph the derivative of it and see where it crosses through the x-axis. Is what you would do for part B. Yeah. Yep. All right. Any other questions from this one? All right. So slide number 4, question C. Is that the snow one? Yeah, okay. So the snow question, what did you say? You said C, right? Yeah, okay. So for the snow question, we've got snow accumulating on a driveway at a rate modeled by f of t is 7t e to the cosine t. T is hours since midnight, and we've got this person, Janet, who starts removing snow at 6 a.m. And yeah, then we've got the rate at which she's removing the snow. Looks like she had to work for 9 hours, or not 9 hours, 3 hours from 6 to 9, fun times. So just real quickly we'll just real quickly do part A. So how many cubic feet of snow accumulated? Well, that's just the integral from 0 to 6 of f of t dt, right? And then the rate of change of the volume of the snow, that ought to just be at 8, that should be f of 8 minus g of 8, right? Rate at which it's falling, rate at which it's accumulating, or rate at which it's being removed. Do that f of 8 minus g of 8. Okay. So then for part C, we're going to have h of t represent the total amount of snow that she has removed from the driveway t hours after midnight. And so we want to express h as a piecewise function with the domain 0 to 9. So we know that h of 0, first off, needs to be 0, right? That's where, that's where we're starting at. At t equals 0, she has removed nothing. And for t greater than or equal to 0, less than 6, right? We still need it to be 0, right? We'll say h still equals 0. Do y'all agree with that? And she's removed nothing from t equals 0 to t equals 6. Then, all right, from t equals 6 to t equals 7, we should be able to write that as 100, the integral of 125. We'll call it, I don't know, we'll call it dx, and we'll integrate from, not from 0, from 6 to whatever t value we're looking at. And so that means that that look like a t. If we integrate that, we end up with 125 t minus 125 times 6, or we could write that as 125 times t minus 6. So from 6 to 7, and it should be the amount that was removed prior to that, which is 0 plus that, which is just this. So that's what it would be from 6 to 7, right? So anytime from 6 to 7, she's removing it at 125.
So then if it's from 6 to 7, why is the upper limit t and not 7?
Because it has to be valid for any time between 6 and 7. And so we're choosing, so we're going to say for, I should have written this here, for t less than 7 greater than or equal to 6, it should be this value, right? So that if I wanted to know how much she'd removed after half an hour, from 6 to 6:30 a.m., we do 6 to 6.5, right? Or I could put in 6.75 up here, or figure out how long it's in 45 minutes. But it has to just be some variable up there to represent a t value on our range, right? Because we're not looking for how much did she remove. We want a function to represent how much she moved given any t value.
Okay, got it. Thank you.
Mm-hmm. All right, cool. So then from there, we just need to do the stuff from 7 to 9. So for t less than or equal to 9, greater than, was it greater than or equal to 7? Right? Hold on one second. Okay, sorry about that. Having an issue with one of my children. So from t equals 7 to t equals 9, we need to first represent how much has already been removed. So we need to have the value at h of 7. And then we'll add to that then the integral from 7 to t of whatever the previous function that we, or not the previous function, but the function that we just got was a 108, I think, dx. And so h of 7, the amount that was removed all the way up until 7, is the amount at, if we plug in a value here, that should just be 125, right? That's what h of 7 should be, 125 times 7 minus 6. So this should be 125 plus, on it, we'll integrate this. So this should be 108t minus 108 times 7, or 125 plus 108 times t minus 7. And so that ought to tell us between 7 and 9 exactly how much we have. And so we would then write out our function as h of t is equal to 0 if t is less than 6, greater than or equal to 0. It's equal to, what was it, 125 times t minus 6, I think is what we had for the next one. That's just less than 7. Oh no, it was greater than. I gotta get my signs right here. There we go. And then the last one was 125 plus 108 times t minus 7. And that would be for t greater than 7, less than or equal to 9. Does that make sense? So it's the amount in the previous section, and then the amount in here that's removed at the rate that was given to us. So it was 0 plus 125 times t minus 6, so that way we just get 125 times something between 0 and 1. And then here we get something between 7 and 9. So we'll get a value between 0 and 2 for the 2 hours times the 108, which is the rate, plus the 125 that was removed in the hour from 6 to 7. Does that make sense or no?
In the original question, the signs were like different for the 6 to 7 and 7 to 9. Like, does that matter? Like, is it supposed to be different? Like it was t is greater than or equal to 7 and less than or equal to 9. Are they supposed to change or no?
Did they change? I may have just written them incorrectly to begin with. Oh, no, here. Oh, yeah. So, I mean, it changes to 108 at t equals 7, but for this full first hour, we're still at 125. So, yeah, I guess I wrote 6. Yeah, I mean, yeah, they are technically, you'd want to change it here so that this is accurate all the way up until 7, so that we know that as soon as we got to t equals 7, we had made it 125, whatever that was, cubic feet, I guess cubic feet probably of snow that was removed, all the way up to 7. And then once we get past 7, we use this one, because if we try to use this one, and I guess if we use this one at 7, it's fine. So you could have left this as an inclusive one. It just makes it hard to get this value of 125 here, because you can't ever actually get to 7 here. If you made this just less than 7, you can't actually get to the 125 that you were supposed to get to. So we flip it around. I think if you put this as a less than and this is a less than or equal to, you'd probably still be fine. I don't think they would have dinged you for that. And I know Riley asked, yeah, you need to show some of the work. If you don't show any of the work in between, they're not going to give you the points. They'll give you probably 1 point at the end for that, but they won't give you all the points throughout. They want to see some integrals written out and all that stuff.
Can you also do D for this question?
Sure. So part D said how many cubic feet of snow are on the driveway at 9 a.m. So that ought to be the amount that accumulates, which should just be the integral from 0 to 9 of f of t dt minus our value for h of 9, which is how much she removed. Sorry, f of t is the rate at which it is accumulating. And h of 9 for us is how much she has removed by 9 hours. And so I don't know what the integral from 0 to 9 of f of t dt is, but h of 9 we should be able to figure out because we can just plug it into here. I plug in 9, that's 125 plus 216. So you'll just do that integral on your calculator minus our value for h of 9, which scoring guide says comes out to be 26.334 cubic feet. Does that make sense or no?
Yeah.
Cool. All right, any other questions before we start the quiz?
Where is in the question with the cylindrical and water tank, where is using the equation of the volume like important? I didn't really know where to use volume.
You're talking about this one that we did yesterday?
No, the next one. The one with the actual model.
This one?
No, the one with the second, that one.
Oh, okay. You called it a water tank, but it was, they're calling it swimming. I went by it because I was like, oh, not that one. Because you're,
I knew it had water, sorry.
All right. What's your question about it?
So like I was kind of able to work through them, but then I realized that I wasn't really using the equation for volume, and I just didn't really like understand when it was relevant, like when you needed to consider the actual volume of the tank.
Let's see. You use the midpoint Riemann sum. You definitely won't need to do that one. Calculate the total amount of water that leaks out. No, you won't need to do that. Part C. Use your results from part A and B to approximate the volume of the water. You shouldn't need it for that. Part D, find the rate at which the volume of water in the pool is. Yeah, you'll need it for this one. For part D. So find the rate at which the volume of water in the pool is increasing. You're going to have to go in and say that your volume, which you know is pi times the radius squared times the height. What was the radius? 12, so 144 pi h. And so you'll do dv dt equals 144 pi dh dt. And then yeah, so I mean that's where you'll use that equation. That's the only place you'll end up needing to use it.
Okay.
Does that make sense?
Yeah.
Yeah, and so you'll have already found, so you'll have found dv dt at t equals 8, and then you'll be able to use that to plug it in there to find dh dt. Good or no? I guess that's a yes. I don't know. Any other questions? All right. I assume that means we are ready to take the quiz.